Today we're going to be looking at the forced vibration differential equation. You'll recall from the last time we were together, we looked at the free vibration system, right? Where your differential equation had this form here and it was equal to 0. For a differential equation that looked like this, what we did was we then went and found a solution y equals to some value. Now, this solution y for your free system where f of x is 0 or your right hand side of the equation is 0 is also called the complementary function. So we can write it like this and we call it complementary function. This is going to become important when we now move to the forced vibration system. So in the forced system, you'll have the differential equation equal to some function f of x where your f of x is not 0. Because of course if it is 0 then you're actually looking at the free system. Now for the forced system your solution y is going to be made up of a complementary function and what we call the particular integral. So this piece here, that is called the particular integral. Okay, now I'm going to convert the differential equation into the operator form just because it's easier to work with. So from this equation up here, I'm going to write this as a d squared bd plus c y equals f of x, right? And we remember in d operator notation, the big D stands for d dx of y, and d squared is just the second derivative of y, okay? Now, your solution for y in your forced system here, the solution for that one there is going to be made up of two parts, as I said before, okay? So, if I put in for y, I replace it with this sum here. You're going to get y, your complementary function plus particular integral equals f of x, right? Which means that a d squared b d plus c times your complementary function plus that expression there, d squared bd plus c y pi is going to be equal to f of x, right? But this piece here is equal to 0. We know that because that is the solution for your free system, the system here, right? Which means that your particular integral has to be equal to f of x, which means a d squared bd plus c times y pi is equal to f of x. And this is what we're going to use in order to find out what y pi is. Okay, and we're going to use a method called the method of undetermined coefficients. So this is the method we're going to be using. Okay, in order for us to find YPI. Now, it's always easier to do it using an example. You understand it a bit better. So let's look at the first example. Let's see our first example. All right, so the first example we're going to look at is going to be plus dy dx minus 2y equals to 4. Okay, if we change that into the operator notation, then it's going to look like this, equals to 4, right? And then you remember we use the auxiliary equation in order to find your complementary function. So in this case, the auxiliary equation is going to be d squared plus d minus 2 equals to 0, right? And you're going to find you'll have two roots, 2 and 1. That'll be plus minus, which means d is going to be minus 2 or d is going to be 1. Right? And you remember again from the previous lesson, you've got roots which are real and different, which means that your form for the solution is going to be ae minus 2x be to the x. Right? And before, because we were working with a free system, this is the same as your final solution for y. But because we have a forced system, you see here, your function f of x is not 0, it's 4. You now have a solution made up of your particular integral as well as your complementary function. So the complementary function is going to look like that. Now we need to find out what the particular integral is going to be. So we know it'll be the auxiliary equation times y pi has to be equal to 4. Okay, so I can write this as this minus 2y pi equals to 4. Okay, and this notation, the d operator notation, this means that you're looking at the second derivative of the particular integral, and this is going to be the first derivative of the particular integral. Okay, so it means that there is some expression for the particular integral so that when you find the first derivative and you find the second derivative and then substitute into this equation, when you simplify, it has to be equal to 4. Okay, so using the method of undetermined coefficients, we're going to guess what y pi is. And in this case, it's going to be safe to guess that it's going to be some kind of constant value. So I'm going to choose the constant to be k, some constant k, right? Which means that the derivative of y pi is going to be 0, and the second derivative of y pi is also going to be 0, right? Now, this guessing of a function is very similar to the idea of a tau function. If you go ahead and do stress analysis, looking at finite element method, they will always speak about a trial function there. So you test to see whether or not the function is going to work. If it doesn't, then you go ahead and you guess a different function. Okay, so now that we've got a form for y pi, and we've got the first derivative and the second derivative, we can now take these values and substitute it into our equation in order to find a value for k. So what we'll get, if we substitute into, let's call it this one here, equation 1. So we substitute into 1, and we are going to get the second derivative is 0, right? The first derivative is also 0, and y pi is k, and that would be equal to 4, which means that the value for k is going to be minus 2, right? Which means that y pi is going to be minus 2. Then the overall solution for y is going to be the complementary function plus the particular integral, which is going to be the complementary function we found here, which is a e to the minus 2x plus b e to the x plus the particular integral, which in this case is minus 2. Right? And that would be the general solution for this particular problem. So that is the general solution. If you were now given initial conditions, you could then go ahead and find your particular solution for the differential equation. Okay. Now, let's move on to the next example. And your next example, we have number 2, 2 times d squared y dx squared minus 11 dy dx plus 12y equals 3x minus 2. Okay, we have second order differential equation, right, is equal to some function f of x, right? Now you remember when we started off with differential equations in class, I always said the first thing you have to do is figure out what your variables are. So let's go back to that. So in this case, the dependent variable is going to be y, your independent variable is going to be x, right? You have a second order differential equation, which means that all the methods that you learned for first order are not going to work. Okay, you have this equal to some function f of x, which means you are working with a forced system. Right? So let me change this again into the d operator form so that it's a bit easier to work with. So we've got 2d squared minus 11d plus 12 times y equals 3x minus 2, right? So we are going to look at the auxiliary equation, which in this case is 2d squared minus 11d plus 12 equals to 0, right? And you can either prime factorize or you can use the quadratic equation formula. And the solution in this case is going to be d equals to 3 over 2, d equals to 4. Your roots again are real and different, which means the complementary function is going to be a e 3 over 2x plus b e 4x. Okay, now let's move on to the particular integral. So the particular integral is going to be 2d squared 11d plus 12 times ypi equals 3x minus 2, right? Which means that there is some function ypi, so that if you find ypi equals to some function, if you find the first derivative and you find the second derivative and then substitute it into this equation, when you simplify, it must be equal to 3x minus 2. Right? So because you've got here, this is a polynomial, yeah, of the power 1, which means that your independent variable here is to the power 1. So we can guess again what ypi is going to be. And I'm going to guess that it's going to look something like that. Right? So then the first derivative is going to be equal to c, and the second derivative is going to be 0. Okay? And I'm going to take these and then substitute back into the original equation. So from this equation here, I'm going to say that that is 2d squared ypi, 11d ypi plus 12 ypi, and that has to be equal to 3x minus 2. Okay? So, the second derivative is going to be 0, which means you've got 2 times 0. Your first derivative is equal to some constant value. So that's going to be 11c. YPI, we've assumed, is going to be cx plus d. So it's going to be 12 cx plus d, and all of that is supposed to be equal to 3x minus 2. Okay, so let me rearrange this a little bit. I'm going to put the 12cx first, and then I'm going to put minus 11c plus d. Both of those are constants, so I want them next to one another. That's 3x minus 2. Okay, so now what we need to do is we need to find the coefficients of c and d. And the way we do that is because we've got an equation, the left-hand side is supposed to equal the right-hand side of the equation. And how do you do that? It means that all your like terms on the left-hand side must equal to the like terms on your right-hand side. So it means that the x terms must be equal to one another, right? It means all your constant terms, so this one here must be equal to minus 2. And we can use that to our advantage to find our constant values. So it means that 12cx must equal to 3x. And the only way that is possible is if your c is equal to a quarter. Okay? Then your constant values must be equal to one another. So minus 11c plus d must be equal to minus 2. Right? You know what c is. C is a quarter, which means when you substitute in, you're going to find that your d value is going to be 1 over 16. Okay? So, taking those constant values, we can now determine what the particular integral is. Right? So, if we look back at the form we had for the particular integral, it was this form here. Right? So, ypi was cx plus d. We now know that c is a quarter and d is 1 over 16, which means ypi is going to be 1 over 4x, 1 over 16. Right? That means the final solution is going to be the complementary function plus ypi, and it is going to be ae 3 over 2x plus be to the 4x, 1 over 4x, 1 over 16. And that is the solution. You can check to see whether or not your answer is correct, because if your answer is correct, you can take the value for y, find your first derivative of y, find your second derivative of y, substitute into this equation. When you simplify, the left-hand side must equal the right-hand side of the equation. Okay, now the method for undetermined coefficients, what we've done is we've actually gone through the first two of, let's say, a template that you can work with, right? So the first one was where your function f of x is equal to some constant value. So if you look at the first example was you have your differential equation, right, equal to some constant value here. So this over here, that is f of x, right? When you've got it equal to some constant, you assume that your ypi is going to have the form of k, right? Now there is a snag case, which I'm going to come to in a later video, which you also have to bear in mind. right? The second case is where your function f of x is equal to some polynomial function. So in the second example you had the differential equation here equal to a polynomial. In this case here, the power of the polynomial was 1, right? So it was a linear value. So this here was f of x, right? So according to the general table, if your function f of x is equal to a polynomial, then you can assume that ypi is also going to have the form of the polynomial. And the polynomial of ypi would have the same power as the polynomial of f of x, just like in the example. So we had f of x was to the power 1. The assumption for ypi was also to the power 1. Okay, now this table I found in John Bird's Higher Engineering Mathematics. I will put up an extract of that book. Okay, in the next videos we will continue with 2 more examples for C and D. In the meantime, you can practice on your own. See whether or not you can get the answer to the following. Let's do first one, 2 dx squared x equals to 6. Second one, dy dx minus 2y 3x minus 2. And then the third one is going to be, I'm just using different notation, y dash minus 2y equals to x squared. Okay, so you try those 3 and see what answers you get. The solutions for these are in the lecture notes that I've put up for you. And that's the end of the session. In the next one, we'll move on to the next 2